Welcome to this explainer. Today, we're taking a huge journey. We're going to trace a path all the way from Earth's ancient, violent volcanic beginnings right up to the complex industrial chemistry that actually powers our modern cities and vehicles. If you've ever wanted to understand exactly how the planet's deep past connects to the fuel sitting in your car right now and what that means for the future of our climate, well, you're in exactly the right place. We've got a great roadmap today. We'll kick things off with Earth's early atmosphere, then break down the greenhouse effect. From there, we'll dive into crude oil and distillation, check out the real-world consequences of combustion, and finally wrap up with cracking and the engineering of future fuels. Let's get right into it. Section 1. Earth's early atmosphere, the volcanic Earth. We're rewinding the clock billions of years to a time when the Earth's surface was completely molten. For millions of years, there was absolutely no protective atmosphere. It was just a hostile, glowing rock floating out in space. Now picture this. As the Earth finally began to cool and form landmasses, intense volcanic eruptions were just everywhere. They were violently spewing massive amounts of gases from deep inside the Earth's interior. But because our planet has gravity, all those gases didn't just drift off into outer space. They were held close, and they formed our very first atmosphere. By analyzing ancient minerals, scientists know this early atmosphere was incredibly rich in carbon dioxide and water vapor, with basically zero oxygen. Honestly, it looked a whole lot like the atmospheres you'd see on Venus or Mars today. So, how do we get from a toxic rock to the vibrant world we know today? Well, as the Earth kept cooling down, all that gaseous water vapor finally condensed. It fell as rain, filling the massive basins to form our first oceans. Now, carbon dioxide is highly water-soluble. It's actually the exact same science that puts the fizz in your sodas, so massive amounts of it dissolved right into those new oceans, precipitating out and forming thick carbonate sediments on the seabed. Then, around 2.7 billion years ago, a real game-changer happened. Marine life and primitive algae evolved. They started using those carbonates to build their shells, and, crucially, they started photosynthesizing. They were locking away carbon dioxide and pumping out fresh oxygen. That biological shift literally re-engineered our entire atmosphere. Which brings us to Section 2, the greenhouse effect. Fast forward to today, and all that ancient carbon we spent billions of years locking away deep underground, we're rapidly digging it up and reintroducing it, which is drastically altering our planet's delicate chemistry. The scientific consensus on the enhanced greenhouse effect is actually pretty straightforward. Shortwave radiation from the sun shoots right through the Earth's atmosphere and warms the surface. Our planet then re-emits that energy as longer-wave infrared radiation, basically heat. But when you have increasing levels of greenhouse gases like carbon dioxide and methane, they act like a giant, invisible blanket. They absorb and trap that longer-wave heat, stopping it from escaping back into space. The result? The Earth slowly but surely heats up. So what's driving all this? Human activities are measurably increasing these trapped gases. The industrialization that gives us our housing, our goods, and our energy relies incredibly heavily on burning fossil fuels, which directly releases carbon dioxide. On top of that, we're cutting down forests, taking away the very plants that naturally absorb that CO2. And meanwhile, rotting waste in massive expanding landfills, plus increased agriculture and animal digestion, and yes, that literally means cow burps, are pumping out huge amounts of methane. Scientists agree this correlates directly with global climate change, driving extreme weather, melting ice caps, and threatening ecosystems worldwide. Section 3. Crude oil and distillation. To really understand the source of these industrial emissions, we need to zoom in from the planetary scale right down to the molecular level. Let's look at where the fuel that runs our world actually comes from. We're pulling crude oil out of the ground, which is a finite resource formed over millions and millions of years from the crushed, pressurized remains of ancient microscopic plants and marine animals. But raw crude oil straight from the ground is just a massive, messy mixture. It's made up of various homologous series, mostly alkanes. Think of these kind of like different lengths of Lego chains, where carbon atoms snap together to form structures of all different sizes. Because they're all tangled up together, raw crude oil isn't very useful until we physically separate these chains based on their size. Enter the fractionating column. Think of it as a giant temperature sorting hat for molecules. The crude oil is heated up until it vaporizes and enters the column. And the setup here is brilliant and highly controlled. It's blazing hot at the bottom, around 350 degrees Celsius, and gets progressively cooler towards the top. The heavy hydrocarbon chains, the ones with really high boiling points, quickly condense back into liquids at the hot bottom. But the smaller, lighter hydrocarbon chains stay as vapors. They keep rising up the column, only condensing when they hit the cooler sections up top. It's amazing, really. This single, elegant physical process gives us an incredible lineup of products. Way up top, we get refinery gases for things like bottled gas. Just below that, gasoline for our cars. Further down, you've got kerosene for jet aircraft, diesel for trucks and buses, thick fuel oil for massive cargo ships, and right at the very bottom, the extremely heavy tar-like bitumen that we use to pave our roads and waterproof our roofs. It's really no exaggeration to say the entire petrochemical industry, born from this one column, is the absolute foundation of modern society. Moving to Section 4, combustion and acid rain. Because extracting and refining these fuels is really only half the story. Taking these hydrocarbons and actually combusting them to release all that stored energy triggers a whole new set of chemical reactions in our atmosphere. How we burn the fuel makes a huge difference. When we have excess oxygen, we get complete combustion. This reaction cleanly breaks the hydrocarbon down into water and carbon dioxide. And while CO2 is a greenhouse gas, it isn't acutely toxic to breathe. But if an engine starves that reaction of oxygen, we get incomplete combustion. And that's bad news. That yields toxic carbon monoxide gas and carbon particulates, essentially soot, that cause severe respiratory issues and create the thick smog you see in big cities. But wait, there is a bit more complexity here. Fossil fuels are organic, meaning they naturally contain sulfur impurities. When you burn them, that sulfur oxidizes into sulfur dioxide. On top of that, the intense heat inside a car engine is literally hot enough to force the nitrogen and oxygen from the surrounding air to react with each other, creating nitrogen oxides. And here's the broader environmental impact. When these sulfur and nitrogen gases rise up into the atmosphere, they dissolve right into rain clouds, forming sulfuric and nitric acids. When that falls back down to Earth as acid rain, it aggressively corrodes metal structures, eats away at limestone buildings, and can completely devastate aquatic ecosystems and crops. To fight back against this severe urban pollution, chemical engineers came up with a brilliant fix: the catalytic converter, which sits right inside a car's exhaust system. The hot exhaust gases are forced over a honeycomb structure coated with transition metals like platinum and palladium. Inside that honeycomb, a super fast sequence of redox reactions takes place. Highly toxic carbon monoxide is oxidized into the much less harmful carbon dioxide, while dangerous nitrogen oxides are reduced back into standard, harmless nitrogen gas before they ever even leave the tailpipe. Section 5. Cracking and future fuels. Because even with perfect combustion and fancy exhaust treatments, the global energy market has a huge supply and demand problem when it comes to those crude oil fractions we talked about earlier. Here's the reality. The world demands way more gasoline to power cars than it does heavy fuel oil to power ships. But nature doesn't just hand us crude oil in those exact convenient proportions. So chemical engineers step in with a process called cracking. They take the surplus heavy, long-chain hydrocarbons, vaporize them, and run them over a scorching hot aluminum oxide catalyst. This thermal decomposition literally snaps those long covalent bonds in half, breaking them down into smaller, highly demanded alkanes for fuel and alkenes, which are absolutely crucial for manufacturing plastics. So as we look at moving away from finite, polluting fossil fuels, we really have to weigh our options. Hydrogen fuel cells present an amazing opportunity. Hydrogen releases a massive amount of energy per kilogram, and the best part, its combustion produces absolutely zero pollution. The only byproduct is water. But it takes a ton of energy to produce, and since it's a highly pressurized gas or liquid, it's incredibly expensive and really tough to store and transport safely. Contrast that with our historically cheap, easy-to-move fossil fuels, which, as we know, come with the incredibly heavy price of global climate change. We've seen how our planet's atmosphere was initially forged by the raw, violent forces of nature, and then dramatically altered by human industry and our mastery over ancient carbon. So the big question you should take away from this explainer is this: as our energy demands continue to grow, how will our future chemistry and our innovations in alternative fuels ultimately define the next era of our planet? Thanks so much for joining me on this deep dive. Stay curious and keep exploring the science that powers our world.